So last lecture we were looking at longitudinal or tensile stress and strain and Young's modulus of elasticity, and we saw the analogy of the elasticity of a longitudinal material with respect to an ideal spring, and the equivalent spring constant, and how to convert questions in which there are combination of materials under longitudinal stress and strain, uh, how to convert them into a system of equivalent springs. Okay, so let's continue from that point onwards today. Okay, so today we will begin by understanding a situation where there is variable stress and strain or non-uniform stress and strain in the application of integration. So for example, we have a situation of a heavy metallic cylinder or pillar or something hanging under its own weight. This is of mass M, natural length L, area of cross section A, and Young's modulus Y. But because of its own weight, it has an elongation delta L. So we want to find out. So we consider any point inside which is at a distance x from the bottom end. Find stress as a function of x at the point P. And from that we want to find the elongation delta L. Okay, so we go back to core mechanics to understand how to calculate tension at a general point P first, like this. Okay. So the method we apply over here is free body diagram method to find tension T at the point P as a function of x. And from that we'll find stress. Again as a function of x. Okay. Yes, Piyush, that's correct. In this we'll be using integration. But to find the tension, we don't need to use integration. Once we have found the stress, variable stress, then we'll take a variable element. We'll take a differential element. To find the strain in that element, we'll use Hooke's law. And then we will integrate over the entire rod's length to find the net strain. Okay. So basically what we do is we make a free body diagram of this section of the rod. And we understand that tension acting at that point is balancing the weight of this section of the rod. Where this is linear mass density into x. Okay. Now there's a small point here that we should actually write it as m upon L plus delta L. But remember, delta L is small compared to L. So we can just approximate it this way. Okay. So tension as a function of x is becoming mg by L into x. As you can see, it's a linear function. Therefore, stress, longitudinal stress at the point P is this kind of a function. It's a linear function. You can see that stress is maximum at the top point. And stress has the minimum value of 0 at the bottom end. So now next thing that we do here is we apply integration. So what we'll do is we'll take a differential element.
Linear mass density.
Yeah. Actually, linear mass density we don't need. We
Young's
just
modulus.
need to apply Hooke's law to that. Okay. So
Okay.
this element, if we look at it now, this
dx.
element is under the action of tension like this. Okay. So as a result of this tension, this element has got elongated to dx plus
dx.
delta of dx. Okay. So what is
Yes.
happening is that this differential, this has a elongated length of that.
Okay.
Some change in dx, whereas its natural length
Yes.
would have been dx. Okay. For this differential element. Just a minute. So this is under strain. Okay. And that should be equal to stress upon Young's modulus. This is the stress. So we can see that the elongation in that element is this much. So we integrate this whole thing now. From x equal to 0 to x equal to L, we'll get the total elongation. This is the elongation of a small element. So integrate the elongation of small element by summation for all these elements will give us the net change in length delta L. Okay. So this will become L square by 2 on putting the limits. Okay. You can see that is the elongation. Okay, so there's also another way to just remember this result, that the stress it's a linear function. So therefore, average stress is minimum stress plus maximum stress divided by 2. That's arithmetic mean of that. So average stress is equal to mg by A is half. So therefore, strain should be average stress divided by Young's modulus. So this result correlate with this. So this is another way of understanding this. Okay, so especially at JEE advanced level, this is quite important. The concept of application of integration when there is variable stress. Just make a note of this. People will continue forward after this.
Sir,
Yes.
sir, can you please show it from the starting?
Yeah, sure.
Can you scroll down?
Okay, people done with this?
No, sir.
Okay.
Sir,
Yes.
how is the natural length of that section dx? Is it of the
How is knee?
differential
It is
element?
defined that way.
It's the okay.
If you cut a small section of the rod, when the rod was not in the stretched position, its length was dx. When it's in a stretched position, it's a little bit more than dx.
Okay. I thought you were talking about the x section, so I was confused.
No, we are not talking. No? See, it's written over there. We are considering the differential element. Its natural length is dx. Its elongated length is dx plus delta of dx.
Okay, sir. Thank you.
Okay. Okay, this is done now.
So, no, the average stress
Yes,
part
sir.
is left.
Yeah, let's write this down.
Sir,
Yes.
sir, so whenever we need to find stress at any point, so we need to integrate that, differentiate that formula.
No, stress is tension divided by area. But stress का formula तो ऊपर लिखा हुआ है. Stress at a point P is mg upon L into x. Na?
हाँ, sir.
That is the stress at any point which is at a distance x.
So we need to only put the value of x.
Hmm.
Okay.
Exactly.
Done, sir.
Okay. Now, next thing we'll see is the concept of elastic potential energy. So the elastic potential energy is stored in a material or a body under stress. Okay. This energy stored, it equals to the work done by an external agent to deform it. To deform it from its natural shape. Just like we had done the derivation for elastic potential energy of a spring, half kx square, something similar over here. So let's say to begin with, you have a longitudinal material which is at natural length. Okay. But now we want to elongate it to a strained length. And in order to do that elongation, what we do is we apply an external force like this. So this work done by the external force is equal to the elastic potential energy stored in it. Now this is the work done by the external agent or external force. Okay. And it is against the internal restorative force. Which is basically the tension. Okay. So going from here to here, the total work done, how we'll calculate. So we'll take some intermediate time. Okay. So at some intermediate stage, if the elongation was just x at that time, and then we increase it slightly by dx. That small displacement dx. Okay. So at this point of time, it was L plus X, whereas now it is increased by a small amount dx. So at this point of time, so in this situation, we can see that stress upon strain is equal to Young's modulus. So the tension in general, or you can also understand it like this, that tension is equivalent spring constant into X, where equivalent spring constant was AY by L. So the external force, just about balancing the tension, so that external force is also AY by L into X. So going from here to here, from this to this, the differential work done by the external this thing is equal to the change in elastic potential energy. So now we understand that the differential change in energy is the work done for that small displacement dx. So it is AY by L into X dx. So the total potential energy stored is the integration of this when we take X from its initial value, which was 0, because we're starting from natural length position, to X equal to delta L, total elongation. So we see the elastic potential energy stored becomes half AY by L into delta L squared, which is basically equivalent to, you can see, half equivalent spring constant into X square, where X is our delta L and equivalent spring constant is AY by L. So you can just remember this formula by analogy with an equivalent spring. So this is also another important concept related with elasticity in stress and strain. Okay. So note this down first, and from this we'll see the concept of energy density, that is energy per unit volume. So we did elastic potential energy in last lecture. Okay. So did we discuss about energy density also, Pratyush?
Yes, sir. Half stress
Okay.
into strain.
So half stress into strain is the energy density.
Yes, sir, we did.
Okay. So then you need not write down this part. From this we can also see that the energy density is okay. So that completes this longitudinal elasticity part. Now we can move on to shearing.
Sir,
So as we have
1 minute,
discussed
can you
before.
go upward?
Sorry,
Sir, 1 minute, can you go upward slide?
we have discussed that in the last lecture.
Yes, sir. Sir, that last line I've
Okay. We discussed all this in the last lecture.
yes, sir. Done, sir.
So if we have body of natural shape like this, which we are bending, like this, we are creating a shear in it because of external force, which is like this. So if this has cross-sectional area A, so here the external force is acting tangentially. Or parallel to the surface. Just a moment. So it acts tangential to the surface. So as we know, the shearing stress is defined as tangential force per unit area, and the angle by which it bends is called the shearing strain. And typically that angle is small. So if this has got displaced by x, this length is L. So you can say that it is approximately tan theta, which is x by L. Okay. So the ratio of shearing stress to shearing strain is called the modulus of rigidity, and that is also material property. So just make a note of this.
Sir, that is new.
Sorry,
So the modulus of rigidity symbol.
the symbol,
Yes.
it is eta. It's like
Eta.
n with a longer stick. That symbol is called eta. It's the Greek symbol. Okay. So now obviously you can see that this will also be in newtons per meter square, right? Because shearing stress is also in Newton per meter square, and strain is always dimensionless. All right, so let's look at a numerical example. So we have situation like this, that a block placed on a rough surface is being pushed by a force, but that external force is applied at the top like this. Okay. And this is a rough surface having a coefficient of friction mu. There's a block of mass m. This length is L. Okay. And this cross-sectional area is E. So given that the mass of the block is 20 kilograms, take G as 10 meters per second square, and the coefficient of friction is 0.6. Okay. So first of all, if F external is applied such that the block does not slide, okay, then find the maximum possible shearing stress. Okay. And if the modulus of rigidity for the material is this much, so this is find the shearing strain for this maximum stress. Okay. So this example combines a little bit of free body diagram concept and mechanics concept, okay, along with this definition of Hooke's law, okay, for shearing. Shearing stress upon shearing strain is equal to modulus of rigidity, and the whole definition of shearing stress is tangential force per unit area of cross section. So just try this out, people. Okay, very good. So I've received the answer from number of you, and seems correct. The maximum shearing stress is about 2.4 into 10 raised by 5 newtons per meter square, and accordingly we'll get the strain by dividing that by the modulus of rigidity. So let's understand. So in general, when we look at the free body diagram of this material, if it is not accelerating, then this external force has to be balanced by static friction. So and the maximum value of static friction is mu n. So the external force should not exceed mu mg. So the maximum external force is equal to, in this case, 0.6 into 200. So 120 newtons. Now this external force, as you can see, is acting tangentially at upper surface whose area is given to us is 5 centimeters square. So the maximum shearing stress will be this mu mg divided by E. So that is this is our maximum shearing stress. So accordingly, shearing strain or the angle by which it bends will be equal to shearing stress divided by modulus of rigidity. So this maximum angle by which it bends be this divided by this is in radians. Okay. So if you want to convert it to degrees, you can see that so that will be approximately point 0.068 degrees. So you can see typical materials like rubber is quite flexible. So the modulus of elasticity is less in comparison to metals. For metals, again, the shearing modulus of elasticity or modulus of rigidity will also be of the similar order of magnitude as Young's modulus, 10 raised power 10 or 10 raised power 11. But rubber is much more flexible, so we have taken the modulus of rigidity of the order of 10 raised power 8. But in spite of that, you can see that the angle of bend is very, very less. It will be hardly detectable to the naked eye even. Okay. All right, so next let's come to the third type of deformity and related elasticity, which is the volumetric stress and strain, or what we simply call volume stress or volume strain. So basically, any body, if under normal atmospheric pressure condition, of course, remember pressure is not a vector quantity. So these arrows are just showing the forces on its
Tensor
surface.
quantity. Tensor quantity.
Yeah, it's a tensor, but we treat it like a scalar quantity here.
Okay.
So, matlab, we treat pressure like a scalar quantity, like we've seen in fluid mechanics. It is normal force per unit area. So normal force is a component of force. So component of a vector is a scalar. Okay. Whereas yes, at a more advanced level of physics, it has to be treated like a tensor quantity, which is
Yes. Tensor ions.
yeah. So if this has a natural volume of V naught under atmospheric pressure, so what will happen is that when it is placed under excess pressure, its volume will tend to contract. So if the pressure is P naught plus delta P, it will have a compressed volume of V naught minus delta V. So the volumetric stress is just written as the excess pressure, and the volumetric strain is the fractional change in volume. Now, in this case, what we do is delta P and delta V are with sign, with algebraic sign. So that means that delta P is positive, means that there is excess pressure. And delta P is negative, means there is deficit of pressure compared to the natural atmospheric pressure. And similarly, delta V is positive, means there is expansion. And delta V is negative, means there is compression. So volumetric strain actually is accordingly written as modulus of delta V by V, and volumetric stress is modulus of delta P. So the ratio of volumetric stress to volumetric strain is the bulk's modulus. So this becomes so to remove the modulus sign, we write a negative sign, because when delta P is positive, delta V should be negative, and vice versa. So the negative sign comes here because if delta P is positive, delta V will be negative. And if delta P is negative, there is deficit of pressure, then there's a volume expansion. So here beta is called the bulk's modulus of elasticity.
Bulk modulus.
And this is a property which we'll see not only for solids, but fluids also, including gases. So in thermodynamics, you would have noticed there are some questions in your module, etc. Not in HC Verma, but some questions in the module which are related to the bulk's modulus for a given type of process. So we'll see how we define it. Okay. So what happens is in solids, the bulk's modulus is a constant quantity, and the ratio of volume, stress, and strain is constant up to what we call the elastic limit of volumetric stress. Okay. But in gases, the value of bulk's modulus actually depends on what kind of process is happening. If a gas is undergoing an isothermal process, it will have a different bulk's modulus compared to if it's going through an adiabatic process or some general polytropic process. So the value of beta for a gas is dependent on the process through which the gas is going, or it's a path dependent quantity. It's not a state function, it's a path function.
So what we have written in that delta P is negative. Then? Sir,
Okay, so again, typical examples. Will involve application of various other concepts to calculate stress and strain. So for example, one type of situation is like this, that suppose we have a container with some kind of fluid, and then we take a solid sphere of rubber or something, and it is submerged to the bottom. So it will be under volumetric stress and strain because of the hydrostatic pressure of the fluid. So if this is an ideal fluid of density, let's say 1.6 gram per cc, and this is total depth of 5 meters. Okay. Now this is a rubber sphere. So rubber's bulk's modulus is given to us as again something like this. Okay. So we have to find first of all the volumetric stress at the depth h for the rubber sphere. And from that the volumetric strain, and then from that the percentage change in its radius compared to its natural shape. Just work this out quickly, people. Okay, very good. Let's check out the calculation. So the volume stress is the hydrostatic pressure. So that's rho gh. So that is 1.6 into 10 raised power 3 into 10 into 5. That's 8 into 10 raised power 4 pascals. So there'll be a negative volume strain. That means there'll be a compression of 4 by 3. So that's 1.33 into 10 raised power minus 4. So negative sign is just showing that it's a volumetric compression. So now you can see that volume is 4 by 3 pi r cube, or volume is proportional to r cube. So delta V by V is 3 times delta R by R. So the percentage change in radius or fractional change in radius will be 1/3 of this. Okay. This is the change in pressure. I mean, this is a percentage change in radius. Okay, so let's move on now. So next thing we'll see is bulk's modulus. For an ideal gas in a thermodynamic process. So we'll develop a general formula for this. So we have this, for example. So you can see that alpha is equal to 1 corresponds to isothermal. Alpha equal to gamma corresponds to adiabatic. Alpha equals to, okay, so any general value like that. Okay, so now you can see that bulk's modulus will be defined as,
So that's gamma, right? Alpha is equal to gamma adiabatic.
yes, we define like this. So so if the gas is going from a state of PV to a state of P plus dP, P plus dV. So during this differential change, okay, during this differential change of state, the volumetric stress the gas is under is dP, that is the change in pressure, and the volumetric strain is dV by V. Okay. And the bulk's modulus is mod of dP divided by dV by V. What's this? So this is the general definition of bulk's modulus. So now if we take the polytropic process, okay, So for PV to the power alpha is constant, okay, change in this quantity should be 0. So dP into V to the power alpha plus P into alpha V to the power alpha minus V, this should be 0. Okay. So if we take V to the power alpha minus 1 common, we have V dP plus alpha P dV is equal to 0. This means that so okay. So this is the general formula for bulk's modulus of elasticity in a general polytropic process. So that is why we say in isothermal process it is equal to the absolute pressure. Okay. And for adiabatic process it is equal to gamma into P.
Sir, the minus here is for the compression, right?
The minus is there because of the modulus sign. No? So when dP is positive, dV should be negative. Okay.
Okay.
When you remove the modulus sign, there will be a minus because dP and dV will have opposite signs. So Okay, so what you can understand from this is that the bulk's modulus is an instantaneous quantity, right? So, for example, we say that a sample of oxygen at pressure equal to 2 atmosphere is undergoing let's say an adiabatic compression. Okay. So what is the bulk's modulus of elasticity for it at that moment? So the bulk's modulus will become, in this case, gamma p, where gamma for oxygen is diatomic. Okay. So gamma will be Cp by Cv. So 7 by 5 into this pressure, which is 2 times. So this is the value of the bulk's modulus. Okay. So at that particular moment, dP upon dV by V will be equal to this. The ratio of change in pressure to fractional change in volume will be equal to negative of this one. Okay, people. So this is the concept of bulk's modulus of elasticity. Okay. So we'll conclude today's lecture a little bit early here today because I have a meeting coming up, which I have to. So
Sir,
this almost completes elasticity. Yes.
sir, I have a doubt in one question.
Yeah. Tell me, Shome.
Sir, in one question you have done that volume is direct proportional to the R cube.
Yeah.
So why you have written like that? Volume equals to 3R there afterwards.
That is a concept of fractional error. Revise that concept that you have learned in the chapter error measurement or fractional change. If a quantity is proportional to another quantity to the power n, then for small changes, we have this relation. Okay. It can be derived from differentiation also, and you have learned it in the chapter of errors.
Okay, sir.
So revise it from there, you'll understand. Okay.
Thank you, sir.
Okay.
Thank you, sir. Bye, sir. Good day.
Okay, so that's it for today's session. Next time we will learn about thermal stress and strain, and from that we will move on to fluid properties, which is surface tension and viscosity. And on completion of surface tension and viscosity, we will keep a lecture aside for discussion of doubts of this whole section. Okay, so make sure you have kept your doubts collected from working out the questions from HCV as well as the module. Okay, that's it for today's session, people. Thank you and wish you all the best.
Thank you, sir. Bye.
Thank you, sir.
Thank you, sir. Thank you, sir.
Okay, people. Bye.